Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This video on sequences is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. In this video, we will be discussing sequences, convergent sequences, bounded sequences, and monotonic sequences. A sequence is a function whose domain is a set of positive integers and whose range is a subset of the real numbers. For example, let's examine a sequence based on the function f of x is equal to x squared. The sequence would be from f of 1, f of 2, f of 3, f of 4, f of 5, and so on to infinity. Or in this case, 1, 4, 9, 16, 25, and so on. The notation S sub n is used to describe a sequence, with n being the successive integers, as in this case S sub n is equal to n squared. A sequence may also be written using set builder notation as n squared enclosed in braces. If S of n is a sequence whose discrete terms n create a range dictated by n squared, then we call f of x is equal to x squared the related function. For example, with the nth term given as S sub n is equal to n plus 1 over n, write the first four terms in the sequence. S sub 1 would be 1 plus 1 over 1, or 2. S sub 2 would be 2 plus 1 over 2, or 3 halves. S sub 3 would be 3 plus 1 over 3, or 4 thirds. S sub 4 would be 4 plus 1 over 4, or 5 over 4. The first four terms is then 2, 3 halves, 4 thirds, and 5 fourths. In another example, let's take a sequence of numbers and find the nth term. In this case, 2, 4, 8, 16, 32, and so on. We first notice that the numbers have a common multiple of 2. Since we see that the sequence progresses more than 2, 4, 6, 8, we conclude that the sequence must be exponential, with a base of 2. Therefore, S sub n would be 2 to the nth power. The related function to this sequence would then be f of x is equal to 2 to the x. Let's look at the behavior of the sequence S sub n equals n over n plus 1. This sequence comes out as 1/2, 2 thirds, 3 fourths, 4 fifths, and so on. This can be graphed against n to observe the behavior of the sequence. Here we observe the sequence getting closer to 1 but never reaching it. We describe this sequence by saying that S sub n equals n over n plus 1 converges to 1. If S sub n converges to L, then L is called the limit of the sequence, and we write the limit as n approaches infinity of S sub n is equal to L. If a sequence converges, it is said to be convergent. Otherwise, it is said to be divergent. Let S sub n be a sequence of real numbers s, and let f be a related function of s. Suppose L is a real number. If the limit as x approaches infinity of f of x equals L, then the limit as n approaches infinity of S sub n also equals L. If L can be shown to be a real number, then S sub n converges to L. If the limit as x approaches infinity of f of x is infinite, then S sub n diverges. If the limit as x approaches infinity of f of x does not exist, then the theorem relating the two limits provides no information about the limit of S sub n. Use the properties of convergent sequences to determine if and where the following sequence converges. S sub n equals 3 over n. This sequence would be 3, 3 over 2, 1, 3 over 4, 3 over 5, and so on. To determine if the sequence converges, we take the limit of the related function, or the limit as n approaches infinity of 3 over n equals 3 times the limit as n approaches infinity of 1 over n, which is 3 times 0, or 0. Therefore, the sequence converges to 0. In some cases, the convergence of a sequence can be found without taking the limit. In these examples, we will evaluate the pattern of the sequence to determine whether the following sequences diverge or converge. S sub n equals the square root of n. This sequence will go 1, square root of 2, square root of 3, 2, square root of 5, square root of 6, and so on. The square root function will affect each one, but the result is the same. The sequence gets larger with each successive n. This sequence, therefore, diverges to infinity. In this next sequence, S sub n equals negative 1/3 to the n. This sequence will go negative 1/3, 1/9, negative 1/27, 1/81, and so on. In this sequence, the negative appears in every other term, but the result is the same. With each successive n, the sequence gets closer to 0. This sequence converges to 0. A sequence S sub n is said to be bounded from above if every term of the sequence is less than or equal to some number m. S sub n is less than or equal to m for all n. A sequence S of n is said to be bounded from below if every term of the sequence is greater than or equal to some number m. S sub n is greater than or equal to m for all n. The following theorems apply. A convergent sequence is bounded, and if a sequence is not bounded from above, or if it is not bounded from below, then it diverges. For example, is the following sequence bounded from above, bounded from below, or neither? S sub n is equal to the natural log of n over n. For this, we consider the related function f of x is equal to the natural log of x over x. We then take the limit as x approaches infinity of f of x, or the limit as x approaches infinity of the natural log of x over x. This gives us infinity over infinity. For this indeterminate form, we can now use L'Hopital's rule and take the same limit using the derivative of the numerator and denominator, or the limit as x approaches infinity of 1 over x over 1, which equals 0. Therefore, since the limit of the related function is 0, the sequence is convergent to 0 and is bounded above and below. If any of the following conditions hold, then a sequence S sub n is said to be monotonic. If S sub n is less than S sub n plus 1 for all n greater than or equal to 1, then the sequence is increasing. If S sub n is less than or equal to S sub n plus 1 for all n greater than or equal to 1, then the sequence is non-decreasing. If S sub n is greater than S sub n plus 1 for all n greater than or equal to 1, then the sequence is decreasing. If S sub n is greater than or equal to S sub n plus 1 for all n greater than or equal to 1, then the sequence is non-increasing. To determine if a sequence is monotonic, apply one of the following. Using an algebraic difference, if S sub n plus 1 minus S sub n is greater than 0 for all n greater than or equal to 1, then the sequence is increasing. If S sub n plus 1 minus S sub n is less than 0 for all n greater than or equal to 1, then the sequence is decreasing. Using an algebraic ratio, if S sub n is greater than 0 for all n greater than or equal to 1, and it can be shown that S sub n plus 1 over S sub n is greater than 1 for all n greater than or equal to 1, then the sequence is increasing. If S sub n is greater than 0 for all n greater than or equal to 1, and it can be shown that S sub n plus 1 over S sub n is less than 1 for all n greater than or equal to 1, then the sequence is decreasing. Using a derivative, if the derivative of the related function S sub n is positive for all x greater than or equal to 1, then the sequence is increasing. If the derivative of the related function S sub n is negative for all x greater than or equal to 1, then the sequence is decreasing. For example, determine if the following sequence is monotonic. If so, determine if it is increasing, non-decreasing, decreasing, or non-increasing. S sub n is equal to 1/3 to the n. For this one, we can use the algebraic ratio S sub n plus 1 over S sub n. For this, we can use S sub 2 over S sub 1, or 1/9 over 1/3, which equals 1 over 3, which is less than 1. Therefore, the sequence is monotonic and decreasing for all n greater than or equal to 1. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you, and good luck with your studies.